G'day, Richard Walding here from Brisbane, Australia. I'm just going to run through a few slides from a presentation I did at the Gold Coast and at University of Queensland. This is the title slide for it. You can see I did it 27th, 28th of November. One was at University of Queensland, which was a Science Teachers Association Chemistry PD Day, and the other was at Griffith University down at the Gold Coast for their Cutting Edge STEM Day for teacher professional development. Now I've called this two great IA2 acid-base equilibrium pracs. Now for Queensland students and teachers, the IA2 is just one of the internal assessments, which is a student experiment. So I'm going to run through some ideas for how that might go, and some ways that you might get something useful out of it for students. So I'll just move on. What I'm going to have a look at are these two pracs. Now I've called them two great acid-base equilibrium pracs. One is a thermometric titration, in other words measuring a temperature, and the other is the conductivity of a weak acid, and I'll go through those. Now the things I'm going to use, well, basically the context for this is something I used to do at when I was an industrial chemist. Now one of my jobs as an industrial chemist was to deal with, in the food preservation industry, particularly at Golden Circle Cannery in Brisbane, and one of the things we were concerned with was canning beetroot. Now beetroot needs a particular pH and acidity, otherwise it'll go off, and you can end up with all sorts of Clostridium bacteria growing. The other one I was involved with was development of a soft drink called creaming soda, which is just a yellowy coloured soft drink. Nothing good in it, it's just sugar and water and nothing much else of any use, but I'll show you a couple of those things in a minute. Okay, let's get back to this. Now I'll go to the first slide, or the first prac, and you can see a couple of things we're going to use. I'll just go through this for a minute. Look, I've opened the can of beetroot. You can see that, in case you're not familiar with beetroot, they're just this particular vegetable here, very dark purpley red colour, and there's the liquid that came off in the can. And you can see it's a purpley coloured liquid. Okay, now like I said, you need to get the pH and the titratable acidity. Now that's the acidity as measured against a acid-base in an acid-base titration against sodium hydroxide. Now I used to do that when I was the chemist. I was a quality control chemist at Golden Circle, and I had to make sure the pH was right and the TA, or the acidity, was right. Okay, so we were looking at basically a pH of around about 3.9 to 4. That would retard or stop the growth of various bacteria, and a titratable acidity of about 0.9% weight volume as measured using in terms of acetic acid. Now that works out to about 0.15 molar. So my job as a chemist was to monitor those two and adjust them if I was able to, and that's not always that easy. Okay, so the way I made it, or the instructions for making it, and it was my job to, when I was told how many litres of syrup they'd need, I'd have to work out how much sugar and all the rest of it just from tables. So typically it was 14,000 litres, so that's like a big rainwater tank of water. It's softened water. Often we used deionized apple juice to get, there's a tax exemption if you're using fruit juice. So Golden Circle would get apple juice, strip all the flavours out of it using an ion exchange resin, and using that as the sugar in the water. Okay, so then I'd get the production team to add about 2.5 litres of 30% acetic. Acetic acid, or it's basically a concentrated vinegar if you like, but it was supplied to Golden Circle, or supplied to the cannery as a 30% solution. Now vinegar that you'd buy in in the shops for using in cooking is about 4% vinegar. Now you can buy cleaning vinegar in the shops as well, and that's about 4 or 5%, and you can buy double strength cleaning vinegar, that's about 8 to 10%. So any of the pracks you do in class, if you want just acetic acid, you could just buy the cleaning vinegar, about 4 or 5%, and standardise it against standard sodium hydroxide. That seems to work. Now of course to all of that we'd have to add sugar to get the sweetness right. So to that 14,000 litres you'd add about 1.7 tonnes of sugar. Now that'd be in bags, so they'd empty the bags in. Now it could be, I don't know how many bags they were, about 25 kg bags, to make up a syrup of about 12%. Now when you think of it, that's a lot of sugar, 1.7 tonnes of sugar. So this baby beetroot liquid was a syrup really. It had a lot of sugar in it, but it also had a lot of vinegar or acetic acid in it. So it was quite a tart sort of syrup, but quite sweet. In fact, I showed you the Golden Circle creaming soda before, and I was holding up the can before. Now that creaming soda has the same sort of pH and titratable acidity and sugar as the vinegar. So really that does, as the syrup in the beetroots. So it's a fairly sweet yet acidic syrup. Okay, now the thing is, it'd be easy to do titratable acidity of creaming soda because it's a pale yellow colour, and if you use phenolphthalein as the indicator, which we do for all of these tests in the laboratory for food, if it's an acid-based titration, try and use phenolphthalein as the indicator. Now you could detect a phenolphthalein change of colour if you're using creaming soda. That's not hard at all. It's pale yellow, and you can easily see when the phenolphthalein goes from clear to pink, because you get a nice pink cloud in the yellow liquid. Okay, the trouble is if you're trying to do the same with creaming soda, with vinegar, you've got this problem. Now, I said before it's a really purpley coloured liquid. If you have a look, I'll just swirl it around a bit and you'll see. Right? You imagine trying to titrate that with creaming soda, with sodium hydroxide and phenolphthalein. You'd never notice the end point. Now you might ask, what's the best way to detect the end point? Well, you could use a pH meter and detect the pH at 8.2. That's the equivalence point we use in industry for those titratable acidities. And when I was doing it, we'd actually stick a pH meter into the liquid and titrate until we got a pH of 8.2, because, as I said, the phenolphthalein wouldn't change colour. Okay, but pH meters aren't the easiest things to use in laboratories. They require calibration all the time. And back when I was doing it, they were pretty primitive sort of pH meters and easy to damage. So we tried to avoid it, but we had no choice. But interestingly enough, you can do another type of titration instead of an acid base, instead of a phenolphthalein one for the endpoint. You can look at the rise in temperature. Now, the equation I've got written in front of us is just sodium hydroxide and hydrochloric acid. Now it forms salt and water, obviously, but there's the heat of heat of reaction, 57.4 kilojoules per mole. Now, when you're titrating, the temperature will rise, and you can detect the end point when the temperature no longer rises. So that seems to work all right. What you can do is use 1 molar, 2 molar hydrochloric and sodium hydroxide as an experiment in class. So my suggestion here is the research question could be, how accurate is a thermometric titration, that is detecting the heat or the temperature rise, in determining the endpoint of an acid-base titration. Okay, so we'll go through some numbers and so on. Now that little meter is just this one here. I'll just show it to you. It's just a digital pH meter, a digital thermometer. Now that reads to 1 decimal place, and it's a little bit more accurate than a glass alcohol in glass thermometer, which would only read to the nearest half division, so that's plus or minus 0.5 of a degree. This reads, because it's a digital scale, you can see on the screen, it'll read to plus or minus 0.1. So I'll just go back to that, and you'll see on the screen I've got 29.0, so that'll read to plus or minus 0.1. Okay, so the range for that reading would be 28.9 to 29.1. Okay, so let's move on to the prac. Oh, before we do, just like to have a look at the syllabus references for Queensland. Now, depending on where you are in the world, you'll have different syllabuses, but in Queensland at least, these are the mandated pracs. So this one here is from the 2019 syllabus when it came out, and it says the mandatory prac is basically just there to calculate the concentration of a solution with reference to a standard solution. So it's just a titration, acid-base titration. Now in the new syllabus that's coming out next year, one of the points, they don't have mandatory pracs anymore. There's just some suggested suggested scientific inquiry points. So investigate the properties of acid and bases. So we're doing that. Now here's the interesting one. Using chemical indicators or pH meters to determine the equivalence point and the observable endpoint. Now normally in class you'd just do an acid-base titration with phenolphthalein. You might even use a pH meter to detect the endpoint. But for this one, we're going to take it a bit further. So that was the mandatory, well, that's a sort of mandatory prac. We're going to make up our own, and we're going to use a thermometer as the indicator for an endpoint, an observable endpoint. Okay, so let's have a look. So here's the setup. Now, I've said in the, you can see the little vial or the little containers, I've got 2 molar hydrochloric and 2 molar sodium hydroxide. Now, I was using 2 molar, so I'd get a reasonable temperature change. The thing I'm worried about or concerned about is the risk assessment. Now, anything up to about 3 molar is not too bad, but students have to check with the teacher about the risk assessment and whether they'll allow that. Sodium hydroxide up around 3 molar is pretty dangerous, and even wearing gloves and goggles and lab coats, it's not something you really want to use too much in a senior chemistry lab. Hydrochloric's not so bad. Okay, and I've got a glass thermometer there. That's a fairly straightforward setup. You could do that with minimal amount of equipment, cost almost nothing because you've got all that stuff. People who are doing it away from a lab, you don't really need a lab for that sort of equipment. You could manage. Okay, so the prac, I made a couple of changes. So instead of using a thermometer, I used a digital thermometer rather than a glass analog thermometer, and you can see I've got my temperature probe into the liquid. Now I've just shown it there at the end point. I used phenolphthalein as well, just to compare, and my burette. So again, back in Unit 1, now I was talking about Unit 3 material there before. Going back into Unit 1, which is for most schools back into the first part of grade 11, year 11, there was a mandatory prac about doing calorimetry to measure the enthalpy of a reaction. Now most schools would do the sodium hydroxide and hydrochloric acid one, comparing solid sodium hydroxide with an aqueous solution and so on. In the new syllabus, molar heat again, doing that, but also there's an experiment where we should be doing calorimetry and heat of neutralization experiments. So it's sort of saying you have to do a neutralization rather than just measuring something dissolving or whatever you're doing earlier. Okay, let's move on. Now this is the prac that I was going to do, or that I did. So I had 20 mils of 1 molar hydrochloric. So I used 1 molar rather than 2, just for safety's sake. I used 1 molar sodium hydroxide in the burette. And the thermometer, as I was mentioning before, I just used the digital one, but you could use a glass, of course. So here's my setup. Now, you'll notice I've got the probe in the liquid. There's the 20 mils of hydrochloric in the flask, if you like. Now, I've used just a plastic cup, partly so that you can see what I was doing. If you use glass does absorb some heat from the reaction, but not a lot. And secondly, I could have put a little cover on that, like a polystyrene cover, to stop any exchange of heat between the environment and the liquid. Doesn't really make any difference, but you could check that out. But I just wanted to show you what the liquid was like inside, and it was easier for me to stir. Okay, so at the start, the temperature was 21.8 plus or minus 0.1, and the volume of sodium hydroxide added was 0 at that stage. Okay, I hadn't added any. Now, at the end point, the indicator end point, when the phenolphthalein changed colour to pink, now that's about a pH of about 8.2, but the temperature had risen to 28.4, so you can see it there. And the volume of sodium hydroxide added was 20 mils, as you'd expect, because they're both around about 1 molar, so you'd expect 20 mils of sodium hydroxide. But then I kept going. I kept adding more of the cool sodium hydroxide from the burette, and of course that's going to bring the temperature back down a bit, not back to the beginning, but it'll bring it down. So here I am after about, I think, 40 mils of sodium hydroxide added, and the temperature dropped back down to 26. Now you'll notice it's not the same as the 21 as the beginning, because we have had heat added from the reaction. Now there's my graph. Now it's pretty much as you'd expect. The temperature rises until the end point at 20 mils of sodium hydroxide, and the temperature levels off. Now I couldn't get anything more accurate than that. I was getting 3 temperatures there which were identical, so it's flat there, so it's not a nice sharp point, but then it goes back down. Okay, now the way you judge the end point as being where the maximum temperature was, obviously it's somewhere along those 3 dots. They're the maximum. The trouble is they're all the same temperature. So how do you judge it? You can take the middle one, which was exactly 20.0, but the way it's normally done with these sorts of titrations is to draw lines up each side and see where they meet. Now I'll just show you what I've done here. So you draw a trend line up each side, and where they cross over, that's called the inflection point, and you can see it's a little bit less than the 20. Okay, so it's on the earlier side, 19 point something, compared to the center point of the 3 temperatures. Okay, now it's not that accurate, but after all, this is a chemistry experiment for senior students. You're not trying to do analytical chemistry for a laboratory. So the students are learning about how these things work and how to make a judgment and justify what they're doing. Okay, so we'll have a look. Now, the inflection point looks like about 19.5 mils. There's some in uncertainty depending on how you adjust these lines. Now, I could move these lines up and down a bit, and it varied around about 19.5, but possibly a little bit under, bit over. I'm saying probably plus or minus 0.3. Okay, now let's have a look at the summary of the results. Now these three here, these three columns, are to do with the precision of the experiment. So it's the uncertainty. Now I've used the delta sign there as a symbol for uncertainty. The physics syllabus uses, the physics reference books use delta, but you don't need to have any symbol. The range is the average plus or minus the uncertainty, and here's the uncertainty expressed as a percent. Okay, now the next thing is the error. We're looking at the accuracy of the experiment, so we're comparing that to the accepted values, and we'll get a error in mils. That's the absolute error. So we've got an EA, A for absolute. We've also got the percentage error, E%. So let's have a look at the phenolphthalein. Now, according to the titer, that actually changed at 20.15 mils. That's where I got the pink colour change. That was stable for 30 seconds. Now the uncertainty for a burette is half a scale division, so it's half of the 0.1, so it's 0.05. So that makes my range 20.15 minus that, which is 20.10, to 20.15 plus 0.05, which is 20.20. The uncertainty expressed as a percent is that value there expressed as a percent of the average, and it's 0.25%. Now I'm calling that the accepted value. We're comparing it to phenolphthalein as the accepted indicator for the endpoint, and the error as a percent. I'm just saying whatever it is, it's the accepted value. So let's now have a look at the maximum temperature. Now that was a bit hard to see, and like I said, but we're taking the middle point. Now it's plus or minus 0.5, so the range is 19.5 to 20.5, and there's my uncertainty. It's the 0.5 for a thermometer divided by 20 times 100. And the error is the difference. Now the accepted error is the absolute error is our value here, 20.0, or the difference between that and the accepted value of 20.15. Okay, so there's a difference of 0.15, and of course it's the absolute, which means you don't worry about whether it's plus or minus. Now that expressed as a percent of the titer is 0.7%. Okay, let's have a look at the inflection method. It was a little bit lower where the points met, the inflection point, and I judged the uncertain to be about 0.3, and so I got a range, I've got an uncertainty and an error percent. Now what you'll notice is this value here is quite low compared to the inflection point, but here that value is quite high compared to this one. So let's try and interpret this. Now the inflection one, we're talking about precision. So this has the lowest or the lower percentage uncertainty of these two. So we're saying this is more precise, and this one here is imprecise, okay, or not as precise, but you can use the word imprecise. In terms of error, you can see this one has the bigger error, so that's not as accurate as this one. So this one is the accurate one, and this one here is inaccurate. Now you can see for students they're able to make some draw some conclusions about the quality of the experiment, the results and so on, and use all their percent errors and percent uncertainties to justify their statements. So I think that works really well. A couple of limitations. Now the equivalence point is 7. That's where the temperatures would have been a maximum. but the endpoint, because it's a acid-base indicator, and its pKa, the phenolphthalein pKa is 9.6. So, you know, the rule of thumb is plus or minus about 1 pKa unit, so, or pH unit. So the endpoint with phenolphthalein is probably 8.6. Now in industry we use 8.2 as the endpoint for a phenolphthalein indicator in a weak acid, strong base titration. Okay, now that's not such a big deal, because when you think about it, going from pH 7 to pH 8.6 takes about 1/100th of a drop of sodium hydroxide. Okay, it's very, very sensitive to changes in OH concentration around about the pH 7 area. So that limitation is hardly worth worrying about. A bigger one is trying to minimise the heat exchange with the environment, and one of the extensions would be using a pH meter in there to identify the equivalents and endpoints. Well, particularly the endpoint where you're getting a pH of 8.2, you're saying that's the indicator endpoint, but you could look at pH 7 as well. Okay. Now, one of the things that happens in industry is, rather than looking at, I'll just go back to that graph and way back here. Okay, what's happening is you've got quite a steep curve, so the rate of change of temperature is fairly consistent, and then all of a sudden there's no rate of change, or it's zero rate of change here. So it goes from a positive number, rate of change, to nothing, and that's at the inflection point. So I'll just go through back to that and show you here. Now you can see the rate of change is flat here, so it's a constant rate of change, and then all of a sudden it goes to nothing at the top of the curve. So if you plot the rate of change of temperature versus the volume, where you get this big drop is actually considered to be the endpoint of the reaction. Okay, now that's called the first derivative. In industry, the machines monitoring the acidity can do this automatically. In fact, in industry they'll have automatic titration machines that measure the temperature. Now they can measure the temperature to, you know, 1/100th of a degree. They've got sophisticated electronics, and they can measure it really low, so they get quite accurate results. But they look at the first derivative, but also you can look at the second derivative, which is the rate of change of the rate of change. Okay, it's another tricky thing, but here the rate of change is nothing, and then you're getting a big rate of change again. So if you look at the rate of change of the rate of change, I circled here to show you the endpoint. If you look at the rate of change of the rate of change, you get a graph like this, and that helps the machines doing the titration to better say where the endpoint is. And again, it's this point just there that I've circled. Now, students wouldn't worry about that, but I just thought I'd try it. Okay, now in Queensland, the heat of neutralisation is a Unit 1 topic. The question is, should this be included in the students' work? And the answer is, well, it's outside the scope of Unit 3. It's molar heats of neutralisation, but you've got enough data to calculate the molar heat of neutralisation, but you can't really use material outside of Unit 3. You can do a few of the calculations, but you can't use the concepts and the theory behind it. So the answer basically is, don't let the students do heat of neutralisation calculations in their student experiment. They'll have enough to do. But I thought I'd have a go anyway. That's the accepted value. Now if you're in Queensland and you're watching this video, you can skip the next few slides because they're just looking at this Unit 1 material. But anyway, delta H is that. Now the H observed is just the amount of heat released per mole. Now we know how much heat was released. We used a thermometer and we had the volumes of liquid and we knew how many moles were reacting. So the number of moles is just the 1 mole of sodium hydroxide or hydrochloric acid. At the end point they were equal, and the volumes were both 20 mils. So the end point was when 0.020 moles of HCl had reacted or 0.020 moles of sodium hydroxide. And so the amount of heat released is just the old MC delta T formula. So the mass at the end point was 20 mils of HCl and 20.15 of sodium hydroxide times the specific heat capacity of the liquid. Now we treat it as water, it's fairly dilute, and that's in joules per gram per degree C, and this is the temperature change at final minus initial, and we're getting 1108 joules released. Now we have to divide that by n, the number of moles, divided by 0.020, and we get 55.4 kilojoules per mole. Now that's plus or minus 3% because of the uncertainty in all our measurements. So the range would be from 53.7 to 55.5, and it doesn't really overlap with the accepted value. Okay, its accepted value is just a little bit higher. So it's pretty good, we're pretty close. The error is about 2 kilojoules per mole. Just take the 2 away, and that's a percent of about 3.6% error. Now that's pretty good. Anything under about 5% in a student experiment for the error is considered pretty good. Okay. Now I did all the theoretical calculations for the whole prac, every mil that was added. You can do it. I won't go through all the details here, but I basically used that same equation and then changed it to delta H times N to work out how much heat was released. Okay, now so depending on how many moles were released, I could work it out at any particular stage of the titration. And this is the actual heat released in terms of the temperature change, and I did the same sort of calculation and worked out the theoretical value of the temperature when I'd added a certain number of mils. Okay, so I think this was at 10 mils of sodium hydroxide added, so the total volume was 30. Okay, now I've done calculations for this in my web page, seniorchem.com, if you want to check all that out. But look, there's the theoretical plot. It looks very much like the one I showed you before from my experimental results. In fact, I can overlay my experimental results and we get this. Now that's pretty good. Look, it's almost perfect. Down here, the experimental values are a bit lower. I think what was happening was I was taking photos and getting the equipment ready for some of the photos, and I think some of the heat could have been lost to the environment, so it dropped a bit lower than it should have. Now, how do we compare the two? Well, actually, you can plot every data point against its theoretical value. It's called a QQ graph. What I do, I plot the theoretical versus the experimental, and if you get a 1:1 correspondence, it means you're spot on. Okay, there's perfect agreement. Now I'm getting a value of, look, 0.9954, so I'm within, well, it's 99.54% of the accepted temperatures, so that's pretty good. And the R squared's pretty low, a little bit of wobble down here when it was coming back down to its original temperature. So the temperatures rose and then came back down. Okay, so that's that. Right, this is the next prac. I'm going to take a break and stop it there.